can check the YouTube.
YouTube is there, but it is not coming till now.
No, it will take
Little bit time, yeah.
10 seconds or so.
Yeah, it's coming now, sir.
This is live now, so people can hear us and
Okay,
see
sure.
us. I'm going mute.
Okay, sure. So I am also going mute exactly at 2 starts.
Hello. Hello.
Yes, sir.
Oh, okay. Just testing. Yeah.
Yes, yes, sir.
Yeah. So how many? So this is an international conference, right? So how many people will be joining in?
Sir, the total registration is around 900. Out of that, 800 is from Indian and 17 countries. As I 17 states.
Mhm.
And 8 countries are there. From there, around 100 participants are there. So total 900 participants yesterday they have registered. Out of that,
So this is an international conference, right? So how many people will be joining in?
sir, the total registration is around 900. Out of that, 800 is from Indian and 17 countries. Sorry, 17 states. And 8 countries are there. So there are,
Mishra, hi everyone. This is Bharani. And,
This a lot of noise coming from somewhere.
Patnaik, is it better, Patnaik?
Yes, sir. Now it is okay.
Okay. Yeah. So since another 3-4 minutes are there, because this is gone. Hi, Shravan. This is Bharani, and I am heading the department of replay department. Welcome you.
Hi, Bernie. Thank you.
Hi. So it's nice
But
to
your
see you
voice is
here.
very feeble. I'm sorry.
Oh,
Voice is
just
very
give me a
feeble.
minute. Just give me a minute.
Yeah.
Yeah. Hi. Is it better now?
Oh, yeah. 100x better.
Yeah. Fine. Yeah. So the thing is, we are, as you are aware, that we are conducting 5 days FDP on recent strategies on micro and smart grid technologies. So I welcome you for the second day as an invited speaker, and for your kind information, this is going live in the YouTube as well. So all the participants are watching us,
Thank you.
and apart from this thing, and
Mm-hmm.
yeah, so so
Mm-hmm.
so what I will say that around, as Mishra has told, around 1,000 participants has registered, and out of which 120 are from abroad, and remaining are from India. And
Mm-hmm.
yesterday was the first day, and Professor Naim from Malaysia has nicely gave us some fundamentals of power systems operations and some real real life experiences as well. He shared with us, and I think
Mm-hmm.
today we are really looking forward for your talk on real time simulation as a key technology enabler
Mm-hmm.
for power systems design, test, and validations.
Mm-hmm.
So I think
Mm-hmm.
we can start giving the introduction. Maybe the Mishra, a formal introduction will begin by Mishra or Patnaik, and from then, so we have around
Mm-hmm.
2 hours of time. So by 4 o'clock, what
Mm-hmm.
we will try to end our session, and then there will be question answers for another 10 minutes or so. Or you can end it up by 3:45, and let's give the 15 minutes
Mm-hmm.
if it doesn't bother you, then you can end it up by
Sure.
3:45,
Mm-hmm.
and then 15 minutes is for the questions, and
Sure.
then the participant will writing the questions,
Sure.
cues what you shared with us. Yeah. So over to
Sure.
Mishra and
So I
Patnaik.
have only one request,
Yeah. Yeah.
Professor Barney. I have only one request.
Yes.
Probably maybe for the first few minutes, I will put my video on, and then
Yeah.
I
Sure.
will
Sure. Yeah.
switch it off
No worries. No worries. No
because
worries.
there will be some
Yeah.
bandwidth issues.
Yeah. No worries. No worries. No worries. As long as
Yeah.
we can hear you, it is enough for us. Yeah.
Yeah.
Okay. Okay.
Yes.
Thank you. Thank you. So over to Patnaik and Mishra.
Thank you, sir. But next, sir, it is mute.
Now am I audible?
Yeah, you're audible, sir.
I'm starting. It's 2 o'clock.
Yeah.
Good afternoon, all the participants. Welcome you all to the second day of the International Online Faculty Development Program, RSMSGT 2020. Today, we have a resource person from Opal RT, Dr. Sravana Kumar, and he will be discussing about the real-time simulation and its importance in power system design, test, and validation. And I assure this will be a very informative session, and I hope all the participants will be interactive. Please post your queries in the chat box, maybe during or post the session, so that after Sir ends his presentation, we will start the question answer session. Now I hand over to Dr. Stithapragya Misra to introduce the resource person and hand over the session to him. Thank you very much.
Thank you, Patnaik, sir. So, on behalf of the organizing committee, I am welcoming Dr. Shravan Kumar, and I am giving brief introduction about him. Dr. Shravan Kumar is currently the team leader at Opal India. Shravan holds a PhD in electrical engineering from Mississippi State University, United States, specializing in power electronics, control, renewable energy, and master degree specializing in electric vehicles, modeling, and simulation. He has more than 15 years of industrial and research experience and has successfully led research and development team in developing many technology products and solutions. He has holds 6 patents 3 trade secrets, and 17 more than 17 international publication and presentation. Thank you, sir, because you have gave us so many times for this one, and on behalf of our whole organizing committee, we are thankful to you. So we can start the session, sir.
Thank you. Thank you, Dr. Mishra. So, 1 second. Uh, good. Good afternoon, good morning, good evening. So wherever you are attending it from, this session. So thank you for the nice introduction. My name is Shravan Kumar, and I'm team lead at Opalati. So uh, today I would like to talk about a very interesting topic called real-time simulations as a key technology enabler for power systems design, test, and validation. So it is a big topic, but my intention is in the next 2 hours probably cover a certain level of nuances of real-time simulations, give a bird's eye view, and to open up the domain and allow the attendees to explore more. So with that, I would start my presentation. So the outline, it's very straightforward. First, I want to introduce on a high level what is the need for real-time simulations, and from the particularly from the modeling and simulation wise, what are some of the rules of thumb. This is very important because at the end of the day, any simulation that we are talking about depends on how we model a particular system. So how to model and what are the some of the aspects we need to consider in the modeling, and what are the different scenarios in real-time simulations. Just give a glimpse about Opalati's hardware and software. Now there are 50 or 100 plus applications or use cases that we have, but I selected only about 8 or 9 use cases. The intention is to uh, give you a feel of how real-time simulations are used in particularly from power applications wise, so that it it gives you an understanding. So let me first, in the interest of the bandwidth, let me just put my video off. Okay. So, okay. So I'll first start off with Opalati. So I know that many is an organization we started off like 23 years back, headquartered in Montreal, Canada, with R&D and sales officers in multiple parts of the world, like in US, it's there in Michigan and Colorado, and France, Germany. In Bangalore, we have it in in India, we have it in Bangalore, and Brazil and China. So right now it's a bit dated number. Right now we have about 270 plus employees worldwide. Uh, and most of these employees are from electrical or electronics and communications background. So most of us are engineers, including from the CEO, who is also the CTO of this organization, and highly technology oriented, and who has worked with in this particular domain, modeling simulation in real times for the last 3 decades, and he has a lot of experience. And he has used that experience to start this organization, and he has slowly built it into um, one of the big entities in this domain. So we have about 500 customers worldwide, and what do we do, or what do we sell or do? We are a leading provider of real-time simulators, and also offer specialized energy services for the power system studies. So here is just a glimpse of some of the industrial customers. Uh, so as you can see, like most of the Fortune 500, whether it is in terms of ABB, GE, Alstom, Dominion Energy, Entergy, uh, so original equipment manufacturers of power system components, as well as the utilities, both in India as well as outside the world, actually use our in some form of the other, either in the design stage or in the final test and validation stage. So similarly, it's not just for industrial people, particularly for the academic folks. So especially for students who are doing research, for the faculty and the PhD students and master students who are doing research. This is heavily used, and as you can see, like most of the IITs are our customers, and also again in as an example, in United States there are many universities, popular universities which do power systems research or power electronics research are customers. So my entire intention of showing this is from twofold. Basically, to make the attendees aware about uh, where who actually uses our products. So it is the original equipment manufacturers of the components, the researchers, and the utility folks are the people who actually use our components. So uh, before I start, I also would like to give a heads up, like starting from this end of this weekend or the end of this week. So we have a 2 days virtual conference called RT20. It's a 24 hours conference. So it's 24 hours because each geography entity, like Opalati India would be doing on June 19th India time, morning time, and June 18th Canada and United States would be doing, and evening time of Canada, which is morning time of the rest of the other continents, would be doing theirs. So feel free to attend this. Please register and attend this conference, and there'll be a lot of discussions, very useful discussions, and useful presentations on applications of real time and some of the lessons learned and so on. So so with that, I would like to start off with uh, here is some information which I took maybe 6 to 8 months back from Wikipedia. So I was just curious and I was searching like what are some of the catastrophic power systems failures we had in the last maybe 2 to 3 decades. So what was interesting is if you actually observe, uh, there is lot many blackouts which are happening. The frequency of the blackouts are actually increased in the last decade. It might not be as severe as it used to be earlier, but if you look at the number of people getting affected or the frequency of the occurrence of these blackouts, it started to increase. Now it could be because of varied reasons. Each country has its own or each blackout would have its own reason, but my entire intention of showing this is uh, as we progress, so there are some systematic changes also which keeps happening in the interconnected network. So power systems is probably one of the mankind's largest network made. So it's a complex network. So what are how the system as such is reacting to multiple changes happening. So what are some of the changes happening if we see, if we take the traditional power grid that we have, or maybe at the transmission level or at the distribution level, anywhere, or maybe even from the generation level, the system, the network by itself is evolving. Like on one hand, you have the aging equipment at the distribution level, transformers, capacitor banks, the lines, so on. At the same time, at the generation level, you probably have so in some countries you have the generators which are probably close to the end of their life, or actually are about to be retired forcefully or not. That's happening. On the other hand, you have a lot of renewable energy at the transmission level, at the big scale level, like megawatt scale parks level, or maybe at the rooftop level, which is a variable renewable energy happening. And there is also a lot of push on going more sustainable. So whether it's renewable or whether it is using the transportation, using the electric vehicles, or using the metros that we have, so as to reduce the pollution and other issues. So all these are happening on one side, and on the other hand, we also have at the home, at the industry, at the consumer level. So there's a lot of penetration of the smartness into the home in terms of the intelligent and communicating devices. So the uh, power consumption is not the same as it was thought about 20-30 years back, where it was more of a constant z load or constant I load. So it is becoming more power electronic based, so constant power based kind of loads. And even there, the pattern of consumption is changing where people are changing the behavior of when they want to switch on, how they want to switch on, and so on. So that is posing challenges in terms of the load forecasting, load pattern understanding, how the load is how the aggregated load is going to look like on the utility at any point of time. So these are some of the things which are happening, and some of the new challenges in the form of cyber security, the cyber physical systems, so which are also coming up. So how to make sure that we continue supplying electricity in an efficient way, in a reliable way, make it available to everybody, but and in a quality way, but at the same time ensure that it is the entities which are providing that are safe and secure, and we are meeting the broader goal of keeping the world green. So the entire power systems, the interconnected system is evolving. So definitely, as we move on, this is how the future power networks is going to look like. As you all know, there's going to be a lot of interaction between, it's not like an electrical engineer any longer sitting in silos when compared to an electronics or a computer science person. Now all these three domains are getting merged, and so it is going to be an amalgamation of those three. So that's how the future power network is going to be more and more. So in those scenarios, how can we address some of these challenges? Now, I'm not saying it is because of these uh, the blackouts or some things are happening, but it is these variabilities, these lot of unpredictable natures, lot of fast changing technologies. How is it going to impact the grid, and how the grid has to co-op itself? So how can we address some of these challenges which are coming up? So the obvious answer always, which is a very generic answer, is to have a robust design and test it and validate it robustly. So from a, that is a generic answer. So what it means is perform efficient analysis of the power system. So whenever we are doing any study, any design development, so try to make that analysis more efficient, more robust. And one of the famous or the best approaches is to use the model based design, the weaker based, which I'm going to talk later. So again, this is that's a known stuff. But what are some of the things to really consider in that aspect? So the first and foremost, okay, if we have to do an efficient analysis, we have to start with an efficient model. So everything starts with the modeling. What are some of the things we need to be careful or look or consider when we do the modeling? First thing is the fidelity of the model of interest. What is the type of simulation that we want to employ? And even in simulation, what are some of the very specific aspects, like what is the type of solver we need to select, the time step we need to select, and computational burden, and do I need to have a parallel processing, or a what kind of processing, and so on and so forth. So these are some of the important aspects which determine the efficacy of a model. So remember, so a model is nothing but an input which gets processed and an output. So the efficient or how efficient our model is, and our analysis, the system analysis is, that efficient will be our the outcomes and the impact that comes out of those outcomes. So once when we have that, so how to test it now? Yes, we test it directly, put it onto the field and test it, or it's not possible in all the cases, and it's not safe as well. So we want to test it in-house in a laboratory environment. But as these different technologies and topologies keep on changing, so what we need to have is a flexible architecture. Hello.
Yes, sir. We can
Okay.
hear you, sir.
Yeah, because I got a sound, so I thought maybe it's disconnected. Okay.
No, no,
So
sir.
flexible architecture, and also which will enable us to test hundreds of what if scenarios. What if there is an n-1 contingency, or what if there is a fault in a converter, or if the controller is not working, and so on. So one of the things to consider is that test bed architecture. And the third one is to uh, one of the things which you need to consider is whatever test bed that we want to do, uh, that should replicate as close as possible to the physical hardware. So why that? Because eventually the goal of having an in-house testing is to ensure that when we put it on the field, uh, the performance is similar, if not similar, as close as possible to the in-house. So how to select the system, or how to model the system in such a way, and how to select the architecture in such a way that we are addressing rightly addressing the issue that we want to test on the field. So there are multiple ways it can be done for that. So one of the options that I'm going to spend more time about is using real-time simulations. So let me start with the first one, model fidelity. Again, so some of these things is pretty obvious, but it is also important. Like when I've seen as a reviewer, as an associate editor of IEEE Access, when I keep looking at some of the articles in the IEEE or some other forums, so many times I see like you know, the problem statement is one, but the methodology employed or the type of model employed to solve that is a different one, or it's not a perfect hand in hand. So that's why I always start with the with this slide. It might be obvious, but it's very important to talk about it for a second. So model fidelity. So model fidelity is the granularity of the kind of model that we are interested, uh, kind of model that we want, which depends on what we want to study. So if I just take as a converter as an example, as a very simple example, now we all know, like we can, as a two-level voltage source converter, I can uh, use uh, uh, three parallel legs with six switches, and it's called the switching bridge model, and we can use it at the same time. We can also use an average model. Uh, Now each is correct in this aspect. It depends on what is the application we want to study. If I am more interested in developing a controller, and which is looking at the harmonics aspect, for example, then for me what is important is to select a switching converter. But again, as an engineer, if I am sure that I do not have any harmonics at a very high order, if an average model is enough because harmonics are induced from elsewhere, then I can select an some other model. It could be average or something, but it depends on what application that we are trying to address. So detailed model typically is pretty good to, like I was saying, the power quality applications, or if we want to study, particularly if there is something uh, wrong in the switch, if one of the switches fails, which is one of the failure mode often in the UPS kind of systems or any of these inverters. So how the system would react, or if you are more interested in looking at the instantaneous responses versus average model, where I'm trying to develop a converter which is not really looking at a uh, that high resolution of the data, but looking at the average level, average over a cycle variation level, then please select that so that your your study will have an applicability. The kind of model that you select will have an applicability on what you want to study. So very quickly, so nature of simulation, again, very straightforward. So instantaneous and phasor. So sometimes I see some of the folks using uh, a detailed model, uh, trying to run it in a phasor kind of environment, phasor systems kind of environment. So it's not that it should not be done, but it is an unnecessary burden on the computation. And more importantly, if your which is being developed, for example, if it's an algorithm development, and this unnecessary jitter from the instantaneous actions would actually confuse your algorithm. So be careful. So what kind of analysis you want to do? Instantaneous, as the name says, you're more interested in instantaneous response of the systems, typically fast transients, and typically used for electromagnetic analysis. And since it's an electromagnetic, we are looking at a very high frequencies. So the time step which is recommended is from 1 nanosecond to 300 microseconds, depending on how fast of the transients you are interested in. So best examples are power quality and applications like microgrid. Phasor, it's typically is used for slow varying phenomena, ideal for electromechanical analysis or power trade or such kind of applications. The typical time steps is other study is 1 millisecond and above. So it's pretty good for stability kind of studies. So long-term stability kind of studies. So uh, the reason for mentioning that obvious thing is coming to this. So it is a very important aspect from based on my experience interacting with many people over the last few years is the methodology of selecting the time step. So the time step, it looks pretty obvious, but believe me, this is the single most, I would say that the one of the highest uh, uh, mistakes made if at all in any simulations. How you select the time step. So the time step should always be selected based on the highest frequency component of interest. So how do I know what is the frequency component of interest? Now there are a couple of ways. Now one which is based on your engineering judgment. So if you don't have any switching converters and if you are looking at a simple 50 hertz system and not much of a dynamics, you would know that unless you have any specific nonlinear loads, you would probably be looking at the max 50 hertz signal only. But if you have a nonlinear hertz like a diode based rectifier and so on, you can assume, okay, I can have 5, 7, 11 kind of harmonics. So what is the harmonic to which I need to filter out my system is an engineering judgment. It's an engineering design question. So versus you can also, if you have a power electronic systems in your model, then you can directly take the switching frequency as the starting point and find out what is the highest component that you would like to capture. So the typical suggestion is select about 5 to 10% of the highest frequency component uh, as the 5 to 10% of the highest frequency component as your time step. So if you are interested in a capturing a frequency of 2 kilohertz, then I suggest please use something like 25 to 50 microseconds, because then you can be sure that okay, you will capture that frequency for sure. Now, if there are switching converters, now I suggest go much lesser so that you don't miss the switching actions or switching events. So I would suggest, if possible, try to go all the way till 1% of the highest frequency of transient. So if you have, say, 1 kilohertz PWM frequency, go till 2 microseconds, or you can play with until 10 microseconds. So the smaller you go, yes, the memory requirement will be increasing. Sorry, but it depends on you can be sure that you will not miss any switching event if that is your region of interest. Now, one of the reasons also mentioning about that in so detail is these 2 points. So typically for power system studies, 50 microseconds is a reasonable time step, unless if there is uh, if the interest is of much lower frequency oscillations like the natural oscillations of 0.2 to 4 hertz, then you can go ahead and select at milliseconds level. But typically 50 microseconds for instantaneous simulations of power systems is pretty good. But there are some exceptions there as well. Like if you take TRV or VFTO studies, so TRV stands for transient recovery voltages. So it is the voltage across a breaker uh, when the breaker starts to open because of any fault or something. So uh, if you see, there will be an initial transient that happens across the breaker, and then it slowly dies down. The extent to which the peak of the transient goes and the settling time of the transient determines the stress on the breaker. So that is very important for the OEMs, the original equipment manufacturers of breakers and other people. So now if you see those TRV studies, the transient is in the range of kilohertz. So you would it's not possible to capture the transient if you are running at 50 microseconds. So but to effectively capture it, you have to go as low as 2 microseconds or 1 microsecond to effectively capture that. Now, in the same power systems application, there's also something called VFTVO, very fast transient over voltages. So this is a study which is typically applied for GIS substations. Now, VFTO deals with the fast transient over voltages that appear across the bushings within a substation. Now, if you see, they are of the order of megahertz. So to effectively capture that, you would actually need to go till nanosecond level. And based on my experience, it is better to go till 1 nanosecond or maybe smaller, like zero 0.5 nanoseconds. I think I have a slide on that which shows that, but it effectively shows uh, how much the smaller times you go, it actually captures the very nicely the transient that appears across the bushing. So this is very important when for GIS kind of substations. So when they are doing the studies. So my entire intention of mentioning this is if you take a TRV study and if you try to put 50 microseconds or maybe 10 microseconds and do a study, yes, you will be able to see some transients, but it's we will not be sure if they are the transient that is going to be observed in actual phenomena. The same is the case with VFTO. Hence, it's very important to select the time step in accordance with the application you have in mind. One of the other things which is also the most important thing what I have observed. So all the things which I'm listing here is based on my experience. So these things are a well-known stuff, but again, so these are the places where we often make mistake. So one of the often things is the IO latency between the hardware and the computer. So we have designed the entire system, we have tuned the controller, it's working perfectly fine, and we want to test it with a controller in the loop, or we want to put the controller outside. Quite often it is observed that many times we miss there is a controller or anything outside and the model which sits in the computer. So now if you look at it, that delay, it need not be only between hardware and the computer, it can also be between the delay caused by the sensors. So in on the field, you have the sensors which would have a delay. So when we design a system in the computer, many times we often ignore those sensor delays. So it's very important to capture that. One of the rules of thumb is try to do um, an analysis over a particular zone. Like I typically recommend from 0 to 10% of your control sampling period, introduce the delay and make sure the design that you are doing still holds good even when the delay of between 0 to 10 sampling period is applied. So what happens is that can account for the sensor delays, the IO delays, and so on. So it's a one good way to ensure before you go to the field that the design is robust in the computer itself. Now, another thing is which I'll be talking about briefly later is on ensuring simulation overall reliability. Now, for as we go to complex systems, it might happen that we would not be able to simulate the system, simulate this, the entire system effectively within the given time step. So we would end up doing parallel processing. So the parallel processing has its own pros and cons. Like for example, it significantly improves the computational speed and impacts the performance, but there is also a the complexity and the memory requirement. And quite often sometimes it would require special solvers and techniques also when we are doing the parallel processing. So on this topic I'll talk a bit briefly later, but in an essence, so it's very important to see how we select a particular model. So is that model correct to the kind of study that I want to do, and is that analysis what I am doing the right type of analysis that I am doing, and is the time step and the the delays and other things which I'm introducing, are they in accordance with what I would anticipate in the field. So if you put these three under consideration, then the model can be a lot more robust. So here is a fictitious example again, which I liked it. So here it shows the importance of, I think I missed the reference. It was probably in white color here. Got, so it shows the importance of the latencies. latency. So is it really important? On the blue curve is a base case or a system which probably you can assume it as a system simulated in models in simulation in computer. And the green dotted curve is the response of the system when a 15 millisecond latency is introduced. Now that latency can be because of the sensor or can be because of iOS or could be because of anything. Now, as you can see, the performance is significantly different. Yes, on the steady state, everything would match, but on the transient level, it's significantly different. So if we are a relay manufacturer, so then I would be very concerned about this kind of delays because it's very important for me, how I effectively look at the transient and ensure that a fault has happened and trigger the breaker accordingly. So this is just to show how important it is, the latency. Now here is another example. Now this is a real example, just to show the impact of wrong sampling time. Um, Again, so this is for a machine example, and what we have here is initially there is a machine drive application where we are trying to control the Q component of the current, and if you see, the blue curve is actually how the system would behave. So, or I would call it, maybe to simply said, I will probably call it an offline simulation. And the red curve is with the real-time simulation. So what we have observed is that there is a difference. There's a significant difference. It might appear small. That's because the axis is of 150 amperes, but there's a significant difference. Now, a lot of time was put on it, like to understand why so it was happening and so on, and it was figured out eventually that it was a simple mistake. It was that the sampling time that was selected was not appropriate. So the moment that sampling time was corrected of the entire model, so we can see that um, the response actually now is very closely matching. So this is just to show or reiterate how important it is. So always consider that as well in your thing. Now, as you can see, so far I've talked about what are some of the uh, very simple, very well known, but some of the important things to consider. I have not talked about solver yet. I will be talking about it in the, I hope I have it in the later slides. Uh, but so even if you look at from the solver perspective, uh, typically we use sustain solver, trapezoidal, but you have forward, backward, and multiple solvers. So please choose the solver in according to what is your application or what is your need. So there are second order models or solvers, there are fifth order solvers. Uh, so if you select a particular solver, uh, it is going to impact on your accuracy. To give you an example, if you know how the exponential uh, the the equation of an exponential is solved, uh, if you take only the first three elements of the exponential, it is like a second order solving, then you will probably end up with a number like 2.5. But if you consider a fifth order solver, then you'll probably come much closer as 2.7165. So how important uh, the accuracy of the solving is for to your design is also something that we need to consider. So solver and integration methods has to be selected accordingly. So with that in mind, so I want to touch to the next chapter of this thing, which is on model-based design. It's a very popular, architecture. I mean, many people are aware about it. If not, so this is an architecture which shows, the stage-wise design of any system. In this context, I'm talking about microgrids, but it could be for any application that you want to design. Now, let me start off with why is that so important? So it is quite often like for, I mean, it could be for even for in our personal lives. If you see, it is very important to identify and rectify any errors in our design in the early phases than realizing them at the end, or maybe as we come close to the end. So if you look at from this curve, which I took from a reference, so this shows the rate of defect discovery and the impact of it. So if this old, or you can say probably, if I'm not employing a robust design methodology, you might end up like a curve like this, the distribution where you will find the discovery of the issues in your design at a much later stage when you come close to the release or close onto the field. Vis-a-vis, if you employ some of these technologies, some of these methodologies, more of like methodologies, you can detect them early during the requirements and design phases itself, and you can correct it. So here, even though the curve shows only like, okay, there is only this much impact or defect prevention, what is important is the time scale is in this way, but the impact on the revenue is on the opposite direction. So there will be a 100x or a significant decrease in the cost of removing the defects when you're doing at the design stage. Now, why is that important? So let's see from the context of a microgrid. Uh, so if I want to start a microgrid, or if I want to develop a microgrid system, it always starts with the requirements analysis. So which is they call the higher level CTQs, critical to quality, which is why is it that I'm doing a particular microgrid to meet what objective? Is it for uh, showing the energy efficiency because the fuel costs are more, or is it more like my criteria is more to show the greenness in the thing, or my criteria is the availability of the power, because in the system where I'm going to put in, the power availability is more important, and energy cost might not be. So best example could be the defense applications. So you start off with the requirements. You clearly identify what are the cost benefit analysis. Typically, this thing is done in interaction um, uh, with the customers, with the objective, understanding the objective, identifying what are the relevant performance standards, technical standards, and so on. And then you start off what we call the the concept and the system modeling. So this probably, if this is a step one, the step two is when actually you start off with okay, I now know the requirements, I now have a clear idea about how what is it I need to address. Now let me start addressing that in the form of modeling the system, start from the concept level. So often that gets done in the offline environment, which is like you take up any simulation software and do it, and observe how the results are coming up in your computer environment. Now the next stage which comes, which is also part of offline simulation, but which is also part of the real-time simulation, which I am going to talk next, is on the design studies. And that's probably the crux of this stage, is the crux of the entire system design and development, which is developing all the necessary algorithms, or identifying, okay, if my design is correct, if I can freeze the design, and all that kind of studies. So all the design related studies, and then we actually go into uh, the implementation in real time. So which is like, okay, I have now my system ready in the computer, it is working fine. So let me first put it as run it in real time, in just only in a real time box, make sure that the system is working fine in any of this when it is decoupled, if I need a parallel processing, or uh, when when I run it in a multi-rate level, because eventually a microgrid or each of these entities is going to be sitting in a different box. So they will have their own sampling and processing speed. So even at the multi-rate environment, my design study is good. And then we go into the different stages of uh, loop testing. So I tested first functionally just for one block, and then I tested as a integrated different blocks, and then final verification and validation. So I'm going to come to this slide in detail next, but this is, if you see, this is a very generic thing. But if you apply it to microgrid, if you can usually see So first we do the individual DR, distributed energy resources control and protection testing, and then we integrate multiple subsystems of that to make it out like a microgrid operation and protection coordination if everything is working in coherence. And then as a final system, you integrate them to a controller, test the overall objective, which is creating multiple scenarios and see how the entire system as is working. So this is a typical process that gets followed. I will be talking more about this in later. So first I would be introducing, if you see there is a blue or a um, gray curve, so which is called the real-time simulation here. So what first I want to do is to introduce what is this real-time simulation and why is it so important from the context of this model-based design. So first I'll be introducing that and I'll be coming back to that later. So simply put, so here is a so what is real-time simulation? Here is a uh, in the desktop environment. Let me take any environment like Link or PSCAD, EMTP, or any of those things. We do simulation here. Uh, if you actually observe, let me take just for the sake of complete description only, I'm just taking that as example, MATLAB Simulink. So I make an IEEE probably 9 bus system and try to run it. Uh, so what we generally observe is even if you want to simulate 1 second, sometimes we observe that the simulation itself will probably take for 10-15 minutes. So 1 second is the simulation, the simulation time, the time we want to observe how the system would respond, but it takes maybe 10 minutes, 10 seconds, whatever to observe that to happen. Why is that happening? That is because the computer environment is working at a different clock, whereas the actual application that you want to do, it has a different clock. So it is useful in some applications, definitely. For some kind of studies, it's definitely very helpful, very useful. Sometimes we see even if you put 100 seconds, it gets entire simulation gets done in 2 seconds. But many times is it is not going to be a true replica of how the system would actually behave on the field. So a system on the field is an actual hardware with an actual Intel processor or AMD processor with its own IOs and so on. So it is going to respond in a different way. So as I was saying earlier, so if we consider those latencies or if we consider those systems, the controller might react in a different way when compared to how it's done in just in the desktop environment. So what is real-time simulation? So real-time simulation is basically a simulation which is not necessarily very fast. It is only fast enough depending on the application. It so if you take consider like electromagnetics, we are talking about the speed of light. So yes, we are interested in at microseconds level, and versus if you're looking at the turbine shaft vibrations, it is at a mechanical time constant, so milliseconds or maybe seconds at level. And if we take a thermostat kind of application, so it's maybe in seconds or minutes. So what is real time is always dependent on the application. So real time simulation means it it is a simulation which must accurately produce all the necessary variables. So both the internal variables and the output variables in a simulation within the same length of time as its physical counterpart would. So what does that mean? So if any system, if you take when we say like something is getting solved in a particular environment, or maybe even in a C code that we write, so we have if I take a simulation for example, so within one time step, it needs to take the input, it needs to do the computations, model computations, matrix solvings, and so on, and then it needs to give the output. So within one time step, it should do that. Now the equations if there is a close resemblance to how a physical counterpart would take in solving that, then what you can say is the simulation that you have is working in real time. Again, it is dependent on the kind of application we are addressing, but the equations and states are solved accurately when in relation or in relativity to the physical counterpart would. So here is a um, clock diagram that I take. So uh, there are so if I start from the bottom, so if this is a computational against the time, this is the computational process computation clock. So I have one computation which is already over. Okay, so it does not start off the so which is probably over at this particular time, but the next computation does not start off immediately. It will wait until the next time step and then start off the next computation, because that is how a real hardware also is going to behave. Now, how does an offline system which is faster than real time, we can say, starts the next calculation here itself. So even though the following time step is here, it starts off here. That is why you can see that the within one time step itself you can have multiple things getting solved. Hence, a 5-second simulation gets solved within sorry, a 5-minute simulation can be probably solved within 5 seconds. Now, for the opposite case where we have a much complex system, sometimes it also happens that you have a larger processor. It is not able to compute all these three stages within the given time. So what happens is it has overrun. That means it started here, it overran its next time step. It is going all the way till here and it will start here. So what happens in this case is many times you miss out the information of what is supposed to happen. Or that can be a converter which is switching in, or that can be a dynamic which is changing, or the state which is changing. So as you can see in both these stages, this is not how an actual hardware would behave like. So hence, it becomes very important. Hence the word real-time simulation, real-time environment, to enable study close to the physical device. So it has become very popular over the last 2-3 decades. So what are some of the benefits of real-time simulation? The first and the foremost is, and it helps us in analyzing various scenarios, operating scenarios, and take necessary corrective actions before actual implementation. Now, uh, you can argue that this is the same thing that even a modeling of a system does. It's correct. Modeling is the first stage, or modeling is the crucial stage of real-time simulation, or for that matter, any simulation. But what it helps is you can be a lot more certain how if actual device would behave when compared to so simply going off with an offline environment and a model which is made. So you can be a lot more confident. So it helps us in reducing the risk, and many times it helps in reducing the cost. Cost can be in the form of equipment or people and so on. And more important, it helps the reliability. So we know with a lot more confidence that this is how the system would behave. Um, it also gives the visibility of how the network would behave in real time. So again, it's got to do with the risk part of it. So it gives a glimpse of if I put a complete microgrid model, if I make a digital twin of it and connect it to a hardware in the loop environment and test it, I can be to a great level certain that I know the controller I have taken care of multiple scenarios and it's going to work fine. So it again reduces the risks. One of the most used uh, application or the benefit is so as we have, if I can give an analogous to a controller or maybe a mobile phone. So there are many OEMs. So if I take a microgrid controller, so there are many organizations. Each organization has its own controller. In the same way, there are many relay OEMs. Each relay has each OEM has their own relay, and everybody says specific to a particular standard, their system would behave in an according way, which is correct. But how do we know if the kind of uh, relay or the kind of hardware that we are going to select is in fact going to work perfectly well for our system. That's one. For our environment, that's one. And the second thing is uh, the testing standards are always within a particular range. So how can we be sure that whatever from different vendors, whatever, if I have a different uh, pieces, how can I be sure like which is the uh, piece that suits my requirement best? So for that, what many test beds were developed, where what they were doing is how to standardize this testing of controllers, relays, or any of these things against a standard platform. So that's one of the most used applications which I will talk about later. So again, it helps in increasing the reliability. So very simply put, fundamentally it helps in reducing the risk in terms of safety, in terms of time, in terms of multiple aspects, helps in reducing the cost, and more importantly increases the reliability, make the design more robust. So the obvious next question is, so is it only in power systems, or if in power systems, where is it used? Um, so where are these useful? So they are useful in, I would say, in power domain for most of the applications, whether it is energy conversion, power generation, microgrids, or in fact cyber security, or whether in terms of the high HVDC kind of transmission using MMCs, or whether we talk about batteries, battery management systems, or smart grid, or maybe electric vehicle. So in a sense, as you can see, it is all about how we apply this design methodology, this kind of principles, and how to make our system more robust. And so applicability wise, it's applicable in most of the places. So so there are multiple scenarios or multiple architectures around it in real-time simulation. So if I can start with the basic building blocks. So simply put, there are three fundamental building blocks of any system. You have a plant, wind plant, solar plant, motor drive, anything. You have a controller, or you have a relay, anything, and you have some sensing element. So these are the three sensing. So these are three um, basic building blocks. Now, it depending on if you put sensors, if you forget about sensors for a second, it is very important. But just out of simplicity, if I can say, if you put sensors to a side for a second, so depending on how we put the plant and the controller, we actually end up with um, four different architectures. So which is what I'm showing here: software in the loop, hardware in the loop, rapid control prototyping, and power hardware in the loop. So what is software in the loop? So software in the loop um, is an architecture where the plant of the system, the controller, and the device under test DUT, or if you don't have any DUT, if the plant and the controller and everything is residing within the same system. What I'm showing here is a real-time simulator box, which I'll talking about it in the coming slides. For now, if you assume that you already know it, so software in the loop is when you have all this plant, controller, and everything on the same environment. Now, what is hardware in the loop? Hardware in the loop is you take out one of these pieces. Now it can be the device under test, or it can be which can be in the form of a controller, it can be a relay, or it can be anything. So the system where you have put in your code, or system which you have developed and you want to test it. So that sits outside, and the rest of the plant, the model, the power system, or power electronics, or everything sits inside this hardware box. So that's called hardware in the loop. Rapid control prototyping is where you just do the opposite of it, where you use the hardware box as a real controller, because it's a real system. So you have the processors and everything according to that, and you have the actual plant, whether it's your motors or solar, wind, and so on, sitting outside. much similar to what we have in the laboratories in many universities. So that's RCP for you. And power hardware in the loop is very similar, is actually similar to hardware in the loop. The only difference is like many times we come across applications where uh, we would like to connect a what do you call a high power hardware, a high power system which is under test to the simulator. So what it does is you have a power amplifier in between. It amplifies the power and gets it to a certain level. So this is how these four, depending on what kind of study or architecture you are doing, uh, these things is followed. The most used are the software in the loop and the hardware in the loop architectures. And hybrid, it's more of just of a concept where you have a mix and match of these different architectures. So what is this? So this is so here I'm showing a one of the simulators of Opalati. So Opalati simulator, and what I'm going to explain now is what exactly happens inside, or what is there inside, and uh, what is the applicability of it. So a real-time simulator. So as I was mentioning earlier, it enables the plant, or enables the system to behave in the same way as close as possible to the physical counterpart. That means it has to take the inputs, process, and give out the output in that speed. That means you need to have a high-end processing technology and high-end internal communications technology, and also the so at the end of the day, this is still a hardware which is based on compiling a C code, or compiling a code which gets generated from the simulation environment that we make. So the having that technology, or having that efficient conversion from the GUI of model based design, or the simulation model, and dumping it onto the code, have the technology or have that system more robust, so that it takes lesser processing time. So that is what actually goes inside a real-time simulator. Essentially, a often the real-time simulator talk from the application of hardware in the loop. If you go here, this architecture, which is the most used architecture, then so that is the application I'm going to talk about. Typically, most of the real-time simulators would have two, uh, I would say, processing elements. One is the CPU, central processing unit. Typically, what we have in our laptops, you can see is here it's much higher end. It's more close to it's actually high performance computing equivalent, and you have an FPGA. So as you know, the FPGA is a field programmable gate array. It is used for very high speed analysis. So it goes at a kilohertz and megahertz level. So and it responds quickly. So hence you can always use it for and for applications or systems or subsystems where you need the time step at much lower level, maybe 250 nanoseconds or much lesser. So again, it depends on if you remember the early of my presentation, I was talking about the importance of a time step and the application. So systems which require fast perform high speed environment, so they are typically simulated using FPGA. CPU is typically simulated at a bit relatively lower speed, and here in this case I'm showing about from 10 microsecond, and it can go above that, 10 to 1 or 5 for 10 microseconds to 1 millisecond, and so on. So a real-time simulator typically hosts these two, and um, it typically hosts, for hardware in the loop kind of architecture, it typically hosts the plant. So what I mean by the plant, so here is a simple microgrid example. Again, we have solar inverter, wind turbine, it can be a natural gas or a diesel generator, and you have a distribution network and interface through multiple controls and so on. If you see this controls part of the solar, wind, and battery and so on, converters and their controls, they are fast acting phenomenon. They are switches based, converters based. So you don't want to miss any switching events. So all these red things are typically simulated in this FPGA, and the rest of the network, which is the distribution network, and the solar or the wind turbine and generator and so on, whose dynamics are much slower when compared to the converters and the kind of things. So they can be simulated in the CPU environment. So here is an example where it shows the CPU environment, which is typically used for phasor or electromagnetic kind of applications. In this case, for microgrid, it does of all the solar, wind, the plant part of it, and this fast switching is done in FPGA. So now, what I wanted to show here is um, there are multiple uh, how to get this plant model and the controls model into the simulator. So there are multiple engineering simulation softwares, just like MATLAB Simulink or PSpice, PSIM, Saber, so on. Um, there are softwares which enable of check it in offline, and with a check of a button and do a couple of actions, you can actually push it or dump it onto a real-time simulator as well. For example, we have HyperSim, eMegaSim, and ePhasor, and as the name shows, so they are typically used for phasor analysis or electromagnetic analysis, uh, or a mix or in the sweet spot of those three. And we have the eFPGA which is typically used for fast power electronics and converter controls and so on. So once when we design, once when we make the plant model in this simulation software, have this check button enabled and couple of actions, so it will dump the plant model onto this simulator box. So moving forward, this simulator box will start acting as if it is a real plant, because the entire system would start behaving in how a typical physical hardware would behave. And then you can in the for a hardware in the loop kind of application, so you can actually interface with your with your device under test, or if, for example, if you're developing your own inverter controllers or drives applications and so on, you can hook them up uh, to the simulator and test it if the controller actions, how is it impacting the plant which is in the simulator. So again, the plant would behave in the speed at which a physical device would behave. So this can, again, it's a bidirectional one. Again, for some applications, we also would need to connect to the exist SCADA or uh, kind of systems. So it is possible to connect these simulators to get SCADA, do some processing, and again send the data back to SCADA thing. So from a decision management level, so we can study real time situations as they are progressing, how is it going to impact, and if the uh, necessary control action which is being taken, if it is if it is acting. uh, that the how it's done. So I think I covered this slide, but information already. But if you just say it again, so how does it actually work? Basically, the simulation platform, it the plant model, it takes in state space level, discretizes it, and solves the equation within the time step, and the input and output. Now, many times it does happen that it's not always possible that within one time step you can do all the calculations. Sometimes, for if you have a complex system would mean like you have a lot of calculations to be done in the form of a parasitic circuit or terms of the complex mathematical equations, then it is not possible even with a very high-end processor to do it on one core or with one CPU. So for that, many times in this kind of an CPU cores or multiple FPGA cores, so it helps. One of the ways to do it is to parallel them, decouple the entire system automatically into multiple systems, each CPU core apart, so that it solves with from the CPU cores and keeps it. This is just the distributed parallel processing, what we typically hear from our computer science friends. So why is that important here? Now, if I take a, a power system, a power transmission level, transmission system. Now, if you see, like I have generation on one side, loads on the other side, and the power gets transmitted through long transmission cables. Many times the distances of them are of hundreds of kilometers. So we know that the electricity is in, or the voltage and current signals are electromagnetic signals. So they propagate at the speed of the light. So the beauty about transmission systems is you have long transmission lines. The long transmission lines, it is a good thing from a parallel processing perspective. Why? Because to decouple the system and make them work in parallel processing, you need to introduce some kind of delay when you are paralleling the system. Sorry. So the good thing about having a long transmission lines is that they act as inherent delays. So if you take 100 kilometers line of a power transmission system, and if you have a wave which propagates, so you can still see, like when you calculate, it will probably end up as 1 or 2 time steps delay for 800 kilometers kind of transmission level. So you can split the network across the transmission line. So you, without introducing any other mathematical artificial delays, so you can parallelly, you can decouple them, solve them in a parallel environment and use it. But how about this? So when you when you come to a microgrid, so typically microgrid, we will be lucky if we have uh, a line of 1 kilometer even. So typically the lines are of very short length. So if I have a complex microgrid like this, what I'm showing here, where I have a microgrid, the two microgrids, microgrid 1 and microgrid 2, connected to a larger distribution network, 210 distribution network. So I how to decouple this entire network, because even if I look at it, the distribution line lengths are very small, the microgrid line lengths are very small. So I do not know how to decouple it and where to decouple it. So in those cases, because there is no inherent delay available, one of the technologies what one would do is to introduce something called a stub line. So I'm not going to detail of this decoupling and so on, because as I was saying earlier, decoupling and parallel processing in itself is a subject of its own. But I just wanted to give a glimpse of what is available. So you introduce a stub line, that means you introduce a short line and select the inductance and capacitances in such a way that you create the time step delay that you want. So if TS is the time step delay that we want, and you already have an inductance of L, so we introduce a delay, we introduce a um, shunt capacitances in such a way that we will be introducing a delay of 1 time step, which helps us in paralleling the in decoupling the entire network and helps us in doing the parallel processing. So in case of voltage source converters and so on, one of the methods is to use the state which is available, which is the bus voltage, split bus capacitance into multiple parallel systems, and we can use it to decouple. So Uh, yeah, so this is how a real-time simulation things work. So if I now get back to uh, the context of the microgrid again, which is the model-based design. So Now, if I take a model, now that we know what is real-time simulation, so it is something, a simulation which helps us to simulate as close as possible to the physical environment. We know what's the hardware in the loop. Hardware in the loop means you have the device and the test, which can be your controller, which can be the relay or something outside. For this discussion, let us assume it's a controller. You have the controller, put it in physical DSP sitting outside, and you have the rest of the microgrid network, that is the plant which is sitting inside the simulator box. So um, so if you, with that as a context, now if you see from a microgrid perspective, I first define what are my requirements. I would like to do an energy management for a rural application. Make sure that the power is available at every time. That's, as an example, is my requirement. Then I start with my offline simulation where I define what is the concept. Should I going to use a two-level kind of voltage source converter with a DC bus architecture, or do I want to I start modeling done in offline environment. Then a part of the study, I start doing analyzing the system, how is it behaving from the power quality and the basic grid interface and energy management perspective. Now, this is also typically done as a part of offline study. Now, if you see, it is from this stage. So when you actually design your start real simulation methodology. Now, this controller, microgrid controller on the it is working so on. So one of the things that I could do is, now that I have my controller ready, let me first test. Let me first make sure that the plant is put it in simulator. Make sure that the controller is working. So put the controller in the outside and see if the controller, the controller that I have designed and I have tuned, if it is working in how I'm expecting when I have it in the DSP level. So the controller would work perfectly fine if I have everything in the MATLAB environment, for example. But the moment I take the code and put it in the DSP, I'll start encountering multiple issues. It could be because of the delays introduced by the DSP and the computer, or it of some inherent issues with the logic itself. Could be. So start introducing start deploying the uh, uh, the design test methodologies of real-time simulation from here itself. And then once when you have that done, keep your entire system in the real-time environment and test it. Make sure that with the IOs and other delays introduced, and with each system looking at multi-rate, like time constants are the physical entities, how the system would behave in the real time. So make sure that the system is working fine. Then move up value, do the individual control and testing of, for example, if I'm doing the solar inverter, okay, make sure that the solar inverter is unit tested. Uh, and then you realize, and then you come back here and do. So that's why this gray curve signifies that wherever if you have an issue, you curved go to the earlier design studies and start implementing, immediately start observing the changes here and going back. So in this way, we can do two things. One, the design by itself, you are trying to make it more robust, even before you go to the final stages of integrated verification and validation. Second thing, you are reducing the amount of time somebody would spend in the design and development. And so that's from the microgrid context. So that is how it can be done. So what I want to show now is two more chapters which are left out. One is very briefly on give a glimpse of what are the different hardware and software that we have. Spend more time on the use cases. This is the different simulation software, as I was mentioning earlier. So it is categorized based on the time step. That means slow time step, 10 to 15 milliseconds on the time step on the x-axis, and the the number of nodes on the y-axis. So if you take, for example, a phasor kind of applications, they are, as you know, they are typically used for hundreds, thousands, and tens of thousands of nodes application, like by day kind of application. And it is they are typically used at 1 millisecond or a 10 millisecond kind of time step, because we are looking at a small signal changes. We are not looking at high frequency changes. So that's one end. Popularity also has, that I was mentioning earlier, eFPGA sim, which is the name signifies, for FPGA kind of simulations which are very fast, typically of the order of time steps 100 to 500 nanoseconds. The inherent limitation of FPGA is the memory. So how big of a network can you solve? It's always a limitation of FPGA. So it is typically less than 100 nodes kind of application. And then you have in the middle the sweet spot, sim and sim, where hypersim is or hypersim and megasim both are used to simulate middle up to about 2000 kind of buses systems, and you can till from micro till above. It need not be only 50, at that. So there are points noted here. So any of this software, so the ePhaser sim, eMega sim, eFPGA sim, all these three together would form part of OpenRT software suite called RT Lab, real-time laboratory. Okay, so they are at the back end is the MATLAB, but all the logics and everything is developed with MATLAB Simulink as backend. And this one, HyperSim, is also OpenRT's thing. It is independent of MATLAB, so it is completely like a EMTP based. So any of the softwares, so once you make it, once you analyze it in offline with certain actions to the real-time box and start testing your design. So these are multiple hardware. I'm not going to go through this hardware, like to put it in a simple way, just like our mobile phones. uh, each of them has its own functional specification, like how many IOs you need, what is the processing speed you need, and so on. According to that, each of these things changes. So so please feel free to visit the website, and you'll get a lot of information on comparison between these. Now, one of the questions that is often asked, and I thought even before somebody asks me, I start these days giving the answer before itself, is which one should I select? So software wise, it is clear, because probably it's more or less I know what kind of application I'm doing. But from the hardware side, which one should I select? Now, or I would say even maybe to a certain level, even from the software side. So the answer to that will be, it depends on you. It depends on the network complexity, the how your architecture, how control architecture is, what are the different, how many hardware interfaces you have, and ultimately what is the kind of application that you are looking at. So it depends on that. Like say for example, here is a 3-inverter microgrid group control, which is made by IIT Bombay. So I just took it as an example. Now this system, microgrid group control, we wanted to test, can it work in my hardware environment called 4510. So if I go back, so 4510 is this box, and I have bigger ones than that as well. So I have a 3-inverter microgrid loop control where I have 2-level voltage source converters, 2 breakers, 6 times ABC to DQ transformation happens, 3 times the droop controls of voltage and current happens. This I want the this entire thing, the controller to be done in 10 microsecond and the FPGA to be at 800 nanoseconds. So I wanted to see if we can do it in this or not. And in this case, yes, we were able to do it. So as I was mentioning, it depends on the complexity of the network and also on your mathematical calculations and so on. So if when we so controller was never an issue because 10 microseconds is good enough for anything. So it is the plant parasites which always drives the or which always causes the issue. In this case, fortunately, we do not have a big parasitics in the form of, if I can say, transformers or in the form of machines. We, in spite of having 3 voltage source converters, that means I have 18 switches and two breakers. So that means 8 switches plus 2. So like 20 state changes, but still this system is not complex enough for a hardware like 4510 to simulate because the parasitics are not that. Now, can I guarantee like something like it will be the same for everything? No. Here is an example for a multi-machine doubly-fed induction machine control. So here we have 4 machines, um, 4 DFIMs. We wanted to kind of simulate something like a wind park example. So we first tried it in 4510. It was not even working on. Why? Because we have 4 machines and we know anything involving a machine and involves a lot of machine and a transformer involves a lot of parasitics. So which takes a lot of computational, which increases the states of the system and takes a lot of computational requirement. So then we slowly start seeing, okay, a system which is as complex as this, where I have 4 machines, 8 converters, 8 transformers, 4 wind turbines, I mean models and so on. So we observed that uh, at the FPGA level, the plant was put in FPGA. It takes about 1.2 microseconds. That means, and at CPU, the converter was put at the controller was put at 20 microseconds. Since we are doing more of an, uh, the speed control of the machine, so we don't need such a high controller speed. Now, one thing to note here, in both these applications, we are using our Eaton software called EFPGA sim. Now you might be wondering, how did we end up with these numbers called 1.2 microseconds for FPGA and in the earlier case 800 nanoseconds. That's one of the beauty of our of the software. So once when you put the system, the plant in the software, it does some analysis and automatically tells you, considering the size of the state variables, I mean the matrix, how much minimum time step is needed to solve it. So for a system as complex as this, then it would need 1.2 microseconds minimum at even at FPGA level to solve it, because here we have considered even the saturations and all those things under consideration. So again, it's not to show this is a limitation or something. It just goes to show that the selection always depends on the network complexity. You can actually put an entire distribution network having 200 lines, 10 transformers also in 4510 kind of environment, but you can also put only 3 machines, but with the most detailed model, and will take up the entire machine, entire simulator space. So that's what it is. So here is on very high level, just to show on the real time. We were checking how we're changing the torque, the load torque, and checking how the speed and machine current was performing. This is just to show how the real time simulation results were actually coming. It's not to show much about it. So here is, so that's about the OPLRT hardware and software. Now, coming to some use cases, I think I have about 6 use cases. 3 of them are particularly on microgrid, addressing different aspects. So, starting with the microgrid real-time example, I think I don't know if some of you would have seen it, then some of you would not have seen it. But as you know, like the distribution systems are becoming more active in the sense that more active control, active network management is happening at the distribution level. The performance and security. So when I say security, it means the energy management in all aspects. It depends on the type of control methodology that we apply, and how the uh, uh, control methodology we apply from energy management and protection perspective. So here is an example which was done completely in Operatis eMegaSim software. So here we have, what we have here, we have a 10 kilowatt wind system. The speed of the wind can be changed through this lever, or you can put a small code for it. And you have a solar system, which is the sun power specs, a real solar system specification. And you also have a lead acid battery based system, lead acid battery interfacing through uh, to the inverter to the thing. And this microgrid, it has 3 local loads in the form of houses. You can change this house ratings, the power ratings, and this entire system was interfaced through a distribution transformer to a much larger distribution network, distribution system, 615 distribution system. So most of them were taken to be like R loads, which is probably a reasonable assumption at the distribution level. So the intention here was twofold. One is to see, one is to model this entire system and make it work in real time. And more importantly, we have created a use case where a fault was introduced at one of the distribution systems, one of the tail end of the distribution system, and observe how the grid islands. And second thing, when the fault was introduced, now many of you would see, so when you say like a 3 cycle fault is introduced at time 2 seconds to 2 to 2.3 seconds or 2.6 seconds, then what real-time simulation enables you is exactly at the real-time clock of 2 seconds a fault happens, and at a real-time clock of 2.6 the fault gets cleared. So we were seeing how this performance of this entire simulation, so with regards to the controller also would look like. So that was the reason why this entire system was developed. And it is just to show, in the interest of time, I'm not going to run through a lot of details of it, but just to show, okay, how the solar irradiation can be changed, and the how the solar power looks like. Similarly, how the wind profile can be changed. So you can give it constant, or you can write a code to change it, and so on. And how the at the point of common coupling, how the wind performance changes. And somewhere at the tail end of the distribution network here, a fault was introduced. So if you see this entire tower is represented by a distribution network, somewhere here we have introduced a fault. So, and that fault, it was a 3-phase line to ground fault, and we observed it to be like for few cycles. And we had 2 observations. One of the first things is the real-time simulation exactly happening the way we wanted it to behave. So the first observation we had was, yes, it is observing, it is behaving in the same way. And second, we did observe some spikes when the fault gets cleared. So of course, in this application, our intention was more on the energy management and studying if the fault is behaving the same way or not. But for any researcher who is interested in seeing, okay, how's the fault clearing mechanism is, or how to coordinate different faults, we have multiple breakers in the system. So this will be a good way to develop the algorithm and test it here. So that's So this is a complete microgrid system which was developed and tested in real-time environment. So as I was mentioning earlier, one of the big use cases for the applications of real-time is on making a vendor neutral test bed. Now, if you look at from a microgrid perspective as well, like there are multiple organizations like Eaton, Schneider, uh, like I used to work at Eaton earlier. So we had our own controller, Schneider has their own, and ABB has their own, and so on. Now each controller has its own functionalities, new functionalities, some modifications. So how can from a power grid perspective or from a top level perspective, how can we standardize the testing of these things so that before anybody buys it, is there a, apart from the standard specifications meeting, can I observe how the controller is really working when I see behaving on my system, on my model, on my environment? So this is so MIT Lincoln Laboratory came up with that concept. So they, along with a consortium, they have developed this test bed. It's called the MIT Lincoln Laboratory Microgrid Laboratory. So if you see, these are the OPLRT simulators which are used to simulate a real power system called Banshee network. And these powers, this so the power system was burnt into this to this simulator targets into the simulators, and these are the input output mapping box, and through this input output mapping box we can actually interface through the here in this case they are showing the Schneider microgrid controller and also the SCL relays, and multiple scenarios were defined. Like for example, multiple scenarios were defined and then tested. Like I am creating a scenario where there is a brownout, or I am creating a scenario where there is a blackout. We can observe, so if there is a blackout scenario, how the controller is of vendor A is behaving with respect to vendor B. So this was helpful in two ways. One, even for the vendors, so or like the Schneiders, ABBs, and other folks, they were able to demonstrate and they were able to learn as well how to improve their system. And for the people who are doing a research, it was like a useful test bed to improve their system. And the people who want to buy it, so they were able to see if this controller is actually meeting their spec or if this is not meeting the specs, and so before that it was more of like everything was only in the offline environment or just going by use case, and then we keep it on the field, but nobody was really sure if this was working or not. So this kind of way was actually helping them to reduce risk a lot. So I think this is just in detail about you know the different uh, real hardware devices which are interfacing with the simulators. Simulator has a distribution network, and this real hardware was interacting with them, and they were testing uh, multiple scenarios. So uh, first use case we have seen about how to design, or not how to design, but more like how real-time simulation can be used in design testing of your of energy management or protection system kind of application. The second use case was more on about developing that generic test bed for microgrid where you can deploy, depending on your application, you can deploy and test it. So there's also one of the very important use case which is called the which is for uh, test. It's called the validation test bed. Now here what I'm showing is from Entergy. Entergy is a utility in United States. So the background of this is almost a decade back or maybe much earlier. So they had multiple intelligent electronic devices. They were being added into the network, and the scenario was that if the vendor has already tested them, and they want to perform more robust testing of the impact of these devices, IEDs, electronic devices, and the the SVCs, the static war compensators, on their network. So how to test it more robustly to make sure that what is being shown is going to really impact their network, the actual utility network positively. So the solution that was employed was to use the OPLRT's hardware in the loop simulator. And here is the right side one, the actual hardware in the loop simulator. Uh, don't get frightened by so many wires going in between. So this is all that mapping box, but this is the simulator which uh, gets mapped with this the actual protection system and the SVC of the Enter-G utility. And so they basically want to test from the IEDs and the commissioning of static power compensators perspective. Uh, is it good enough? What they purchased and what models do they have, is it good enough? So a detailed test was done by us, and so three outcomes have come out of it. One is, as a first stage, it was used for the DFR acceptance testing, design for reliability testing. It was used for that. Second thing, the most important observation was the original relays which were selected for the short series compensation. The relays were found to be inadequate in the sense that they had to what they had in the model, and when they tested, when they selected that particular relay, but was not that good enough. Or I won't say good enough, it's not a correct word, but I would say it's not adequate enough to uh, it was not adequate enough to meet their specs. The third thing, which is one of the most important things, is on this I would like to spend a couple of minutes, is on if you take from a utility perspective, or for that matter, even from an industrial perspective, where the equipment is being used continuously, uh, when the utility or the industry purchases a certain thing. Let me take for example utility. When you have generation system and purchase a particular exciter and governor system, so you get the models along with which the OEMs would provide. You have the tuned setting of these models which were done at the time of installation and commissioning. But over the period of few years, multiple things happen. Uh, is from the regular wear and tear of the machine and of the controller and so on. So, and there is also continuous changes in the network. So if you look at it from a power systems perspective, the network every 3-4 years, the architecture might remain the same, but the kind of new devices or the new uh, technologies that get added to it keeps on changing. So it, we cannot be sure that whatever initial tuning was done by the vendor at the time of installation and commissioning holds good even after 5 years or so, because there's a continuous variability. So how to make sure that we whatever I have, especially from a larger grid perspective, how to keep the system well intact, so that the response, if you take a frequency response perspective, the generator response is in the same way as it was studied at the time of installation and commissioning or so on. So for that, we need to have a detailed models at the time of installation. The vendors typically would provide the models, but quite often, because we're talking about long times in terms of 5 years, 10 years, 15 years, the simulation software themselves get updated. Many times the people who develop the models, they move on, they go to different places, and so it's not a seamless thing that you had to change multiple versions, and we are not sure like what is happening and what. So in a similar way, so that is something is sort of like an issue always with the utilities. One of the things similar to that is the model. Even when you have the model which is made, will that be adequate? So or good enough? So when you actually try to start testing your system, so that was one of the things that was found in this application, which was that. The PSSC model turned out to be good, but it was inadequate. The model did not have some of the necessary features or some of the necessary stuff which gives the more depth analysis of the network when compared to when the system, the SVCs were tested it in real time. So that was also one of the outcome which has come. So this testbed has enabled the utility directly as a utility as a perspective. They have realized that and they started deploying it more and started studying and making sure that they validate it in real time before they start and deploy it in commission. And one of the outcomes as quoted by the utility itself is that it enabled them quicker by about 2 times, 50% faster testing and more robust testing. So as I was mentioning in the beginning of the presentation, this is one of the very important, that was a very important use case or application of trying to make sure whatever you have in the computer level being robustly translated to the product level and deployed, and then maintain it continuously over the period of few days. So coming to the next one, on the microgrid level with a slightly difference is the advanced distribution management system. So I keep using the word test bed because actually these are test beds. You can even though it goes beyond the design stage, it helps you in even in testing the system. So ADMS is a test bed which was developed as a consortium with multiple OEMs and the US Department of Energy, Opel RT, Schneider, and others. So the intention here is early in the presentation I was talking about multiple changes which are happening at the distribution network level and at the transmission level also. So the power network is evolving. So particularly on the distribution side, it is evolving at a much faster pace. Electric vehicles, the smart thermostats, or the rooftop solars, and all those things are starting to come up. The power electronic loads and everything started to come up. So how do we effectively uh, study so many changes which are happening? And how do we effectively design, study, test, and validate those 4 stages? So, and they have identified, this consortium has identified a set of, if I'm not wrong, 16 applications. Yes, 15 applications, I'm sorry. A set of 15 applications were being reviewed, like how a future distribution network would look like. Uh, so from a business case perspective, it helps them to develop not only a vendor neutral test bed, but a design, test, validate platform. So it can be used for so many applications. So one of the applications, what I'm showing here is the application called the VoltVar optimization. Very briefly, so VoltVar is trying to optimally maintain the voltage and the reactive power within the system, so that at the end of the day, the losses are reduced and the high voltage profile is maintained. I mean, the close to flat voltage profile is maintained. So here is that architecture. Uh, we have 2 things which are happening parallelly, or 3 things which are happening parallelly here. One, we have the entire network being on a multi-time scale split into 2 parts. One is the phasor and EMT kind of simulation being done using ePhasor and um, forward, I think ePhasor and Hypersim, if I'm not wrong, but I need to check. So kind of environment, and you also have the OpenDSS tool, which is using the rest of the system. So this is one thing to demonstrate that how you can do a distributed or multi-time scale simulation. Or I would say the co-simulation. So it's also one of the things to showcase. Um, and then you have actual hardware. So the actual hardware we have here are so how do we cause the voltage and the VAR to change in the actual distribution network? You If you forget about the DERs, the solar and wind for a second, then the traditional way we do is through chaining the capacitor banks. So having the capacitor bank controller changing it, or the load tap change transformer. So the controller of that. So we have the controllers of this actual capacitor bank and tap change transformers. So the control. So if you the actual transformer and the actual capacitor bank, the plant of it are in here, but the controllers are sitting outside, and so they are interfacing with with we also have a power hardware in the loop environment where the solar system, the solar inverter is in this case forgot the power level, but the solar inverters, if you assume it is at this level of the plant, you have a, a multi kilowatt level solar inverter which is emulated outside and then integrated into this part of the network. So this is the actual solar inverter which is integrated here, and you have this the actual controller, the controllers of the cap banks and the tap change transformers which are interacting with the network, and you have a centralized database emulated as a SCADA system from distribution grid, and which is taking all the necessary data, the red lines, and then giving out the blue lines, the controls and the feedback to control. So basically you have the SCADA which determines, or you can say the logic which sits here, which starts sending the control signals to these inverters and controllers, and they start responding, and that response appears here in this distribution network. And you can see as the simulation keeps going on, you can start changing your controls and you can observe how the network is behaving. So in this way, so initially a lot of study, maybe a 2-3 years, couple of years study was done on the volt var compensation application, and they have seen what are some of the benefits really to the distribution grid from that application. And I think the uh, other applications would also be done. So my entire intention of talking about this is, if you see in a nutshell, this is you can hypothetically visualize this as one microgrid, and this is as the rest of the network, if you may. And you can effectively analyze multiple applications using one environment. You can not only design, you can start off everything in the design level, start it here, and then you can slowly start branching out, saying, okay, now I have everything in the control, everything in the PC level. Let me put my PV outside, let me put my controller outside the next step, and then at the third step, let me put my the SCADA controller or the central controller outside, and you can see progressively how the system performance is behaving. It's like a flexible architecture. So that's the reason why of me showing this. So, and I think I have only 3 more use cases. Um, so right now, until now, what I've talked about is more about only the microgrid application, which has only like tens of nodes or 100 nodes or uh, such kind of application. But I just wanted to clarify. So there are many applications like wide area monitoring kind of applications where we are talking about 10,000 nodes, 30,000 nodes, so on. Here is an example where I'm showing 108K nodes, that is 1 lakh nodes. So, uh, so as you know, like just here the interest was more on understanding the as the loads changes and different scenarios, what is the impact on the frequency on that. So IEEE 118 bus grid, which was considered. So a lot of so it's a mix of both the transmission and the distribution network. So the entire system was done in 10 milliseconds. So again, why we need 10 milliseconds? Because two things. One, we're talking about 1 lakh nodes. So system comp is that big. Second thing, we are not interested in any instantaneous kind of results here. The interest is more on the larger scale. So now, just to give you a glimpse, or to show that, okay, it's not that everything can be put in one box. Even at 10 milliseconds, to show how complex this model is, it would need 7 CPU cores. So it would need 7 Intel CPU cores at even at 10 milliseconds level to simulate this network in real time and observe. So I just wanted you to get a glimpse or of how complex, how it's the selection of how many cores that you need and how many parallel things that you need is a function of the system complexity, and it is something that I would say it's more customizable. So it has to be worked along with an engineer to find out. Okay, so I am trying to simulate the half of a state utility, then probably I would need maybe 20-30 cores, in parallel combination to do it. So so one of the applications, very quickly, this is more from the power hardware in the loop application. It's on the electric vehicle, uh, providing the ancillary services for distribution company. So again, so this is this I took it from a reference as I'm showing here. My entire intention of talking about this is particularly from India perspective. As we talk more about electric vehicles, we have three research areas that we can immediately look into. One is on the EV battery level itself, which in itself involves battery management systems and designs related to that. And second thing is the impact of this EV per se on the grid charging level, or on the B2G kind of applications, which is the third one, where when you have maybe 10, 20 years from now, when you have more electric vehicles connected to the grid, so you can probably use them for voltage support, you can use them for frequency support or kind of applications, because essentially you're talking about a connected battery. So here was a study done by this particular reference, and what they have shown here is the RMS of a voltage at at the deep end of the at the tail end of the distribution line. That is here, tail end of the distribution line. So before the voltage control, it is expected that the voltage would actually reduce before we start doing uh, in the original case, conventional case. But as we have more electric vehicles, and once when we start using them for the reactive support, then you can closely flatten out the curve. So the moment you flatten out the curve, you will reduce the losses. So here is the test setup that is used by the reference. It's a My intention of showing this is from a PHIL perspective. So they have the actual batteries, uh, EV batteries and the controllers, which are interfaced through a power amplifier, because we're talking about a bit higher power application, and interface to the distribution model. The model is entirely sitting in the simulator, and tested it and shown that okay, here is how we have observed the results even in real time. I think this is probably my my last application, which is um, which is on the cyber physical systems. So I'm not a cyber expert, but one of the upcoming or one of the important aspects to consider is the grid security. And what we have here is a cyber physical system or cyber physical simulation framework, where it enables how you can how you can use the real-time simulators, along with in this case we are partnering with another organization who are experts in the cyber security and network security kind of level. Together as an entity, how we can address or simulate the different cyber physical issues that can come up, and how somebody can take necessary actions to address them. So here in this case, what I'm showing is a very simple power network is simulated in real time using ePhaser. Again, the choice can be HyperSim or any other thing, but as we are talking about cyber security, which is probably in terms of minute scale, I don't need to go to instantaneous. Something like a phasor analysis is good enough for me. So ePhaser sim, and the intention here is to show how a tap changer controller change is going to impact on the network. So the example simulated network is emulated digitally using Exata. So Exata is a software which allows for communication across multiple communication layers. And so I'm not an expert in this, but what I can say is this software Exata, it gives the necessary TCP and IPC signals so that you can interface directly with this virtual sensor of the tap change controller and start changing it. Let us see an example. So here is an example case. Um, I would call it like maybe like a cyber attack. So an attacker intrudes onto a RTU remote telemetry unit of a tap change controller. So the tap change controller will always have an RTU which keeps interacting with the SCADA, right? Now a hacker or a cyber attack guy, he or she intrudes into this RTU. Now, how is the RTU and the tap change controller typically designed? Typically, they are designed to operate within the normal voltage range of 0.97 to 1.03 per unit. So typically, they are designed to operate like that. And when the voltage is outside the normal range for 10 seconds or more, the controller changes the tap position with regards to do you want to increase the voltage or decrease the voltage. So for those of you folks who know about how the tap change transformer looks, so you have multiple studs, and touch point can be, each stud will have I think about 1.66 per unit percent or something, 0.16 percent per change in 0.16% change in the voltage, something like that. So we can keep introducing up to plus 12 or minus 12, and you can increase or decrease the voltage. Now the ideal behavior is if the voltage falls beyond this 0.97 to 1.03, the tap change actually the controller gives a signal, and the physical device would move the stud. Now in this case, what was emulated, it was emulated that the hacker hacked into the RTU. So basically they have hacked into the sensor itself or the communication layer of the sensor, and they kept pushing a message saying, even though the voltage is at 1 per unit, they kept showing a message that the voltage is at 0.96 or 0.95, some number like that. So the controller always assumes that the voltage is much lower, so it starts behaving because that is how it is designed to. So it starts changing uh, the voltage studs of the transformer. It reduces. If, as you can see here, it keeps on changing the changing the stud position. But since the hacker is introducing at the RTU level, the sensing element which goes into the sensor data which goes into the controller still feels that the voltage is at 0.96 only. So you have the controller trying to continuously reduce the tap because the hacker is hacked in between, and eventually beyond a certain level the system collapses. So this is a possible scenario again. So the intention here is not to show that using any of this at least from an OpenRT perspective or from a real-time simulation perspective, intention is not to show that you can prevent using this. No, the intention is to show is to create a scenario how something hacking can be done, creating an environment of how hacking can be done, because you cannot directly go and change a tap changer by ourselves in a utility substation. We can observe how the controller is behaving. So there are multiple things that we can get out of it when you recreate this scenario, like how what changes should I make to the logic of the controller, or if a hacker has hacked in, so what is the kind of signal that we can observe when somebody has hacked in? Maybe something like a signature analysis of something. So it basically paves way for multiple things. And from a computer networking or from a computer or internet IT perspective, how to make it I won't say unhackable, but how to make it more safer. So that's the other intention. So in a nutshell, um, I am a power electronics guy, but I would like to talk more about power systems because that's much closer to me. But so, in a nutshell, what I have talked about is the application of real-time simulation from not just microgrid, but from a power systems applications perspective across multiple layers. Now it can be from the protection layer, it can be from the cyber security layer, it can be from a wide area monitoring through PMUs, anything. So here is just as an example to show as a typical test bed how it would look like if we want to integrate when you try to integrate multiple hardware into it. Like for example, PMUs can be integrated. Yes, you need to have some signal IOs and so on, but just to show that this is possible. And I think this is probably my last slide, so pardon me if you're not able to read it, but uh, what I'm showing here is in the to the interest of many researchers, there are multiple applications, whether you consider the wide area monitoring or protection or distribution grid automation, that is possible through possible to uh, be tested using real-time simulations. So start off your design as shown in the V curve. So when you start designing your system and when you come to a certain level, before you, in fact, you even go to the DSP level, I suggest you try to run your system in real time. Make sure that the necessary, just everything in the hardware box, the software in the loop kind of architecture, the system is working as expected. And then you go to the next architecture where you try to put the device under development or the technology under development outside, test it more robustly, and then deploy it onto the field. So this helps you to make sure that you spend less time on the field, and you don't have to sweat out on the field. You can be more sure that the design will be good. And most important of all, try to make sure when you make the model ultimately for any of these things, um, please follow that very simple basic principles, so that it goes hand in hand with what you're trying to design. With that, I want to once again say, so please feel free to register and log into the RT20 real-time 20 virtual workshop, and there'll be a lot of presentations, discussions, and it's on this 18th and 19th. And yep, so if you have any uh, questions, feel free to email to this email address. I'll get that forwarded email, and also please go through our resource center, and if you have any questions, yeah, please ask me at any time, and I'll see how many I can answer, and if not, I will learn and get back to you. With that, I think I probably conclude. I think it's exactly right, 2 hours. So um, again, so this is as I was telling earlier, this in itself actually should be a course, because there are multiple topics which are still involved in it, like interpolation and how do you select the particular even when you say the solver, how do you select which type of solver and what's the impact of each solver and so on. But I hope this gave a high level glimpse of at least what the game looks like, and you can always build upon that. This I hand it over to the organizers.
Thanks a lot, sir. So now we can start the question answer round. So some question is there. So sir, can I read the question or should I paste the question in the chat box?
No, I think it will be great if you can read the question.
Yeah.
Okay, so first question Dr. D. Satish has sent. What is the difference between switching time TS and sampling time TS?
Switching time TS and sampling time TS. Uh, Basically, both are the same. I think maybe somewhere in the text, maybe I would have, out of oversight, I would have written maybe sampling, but it's just basically it's only one TS time step. So yeah, but otherwise both it's we are talking about the sampling time step only, sampling period only, right? So both should be the same.
Okay, thank you. Second question from that person only. How switching time is affected and simulation circuit?
How switching time step is affecting a simulation circuit.
Simulation circuit. Yeah.
How to say it? So let me probably go through that particular slide. Okay, so time step, if you see, it is just in a discretized system. Within one time step, you have to take input, calculate the whatever mathematical calculations, and give the output. So of course, the core of this is a mathematical calculations. Now, excuse me. So what do we mean by mathematical calculations here? If I have a simple RLC circuit and I have a switch, or then I have two particular. When the switch is on, I have a one kind of matrix. When the switch is off, I have a different kind of matrix, right? And at each time step, now what is the state of that each component? Like the inductor will have the inductor current and the capacitor will have the capacitor voltage, and these states keep on changing. So if I take a time step of 1 microsecond, so within 1 microsecond when the switch is on, so I have a set of equations which I need to solve, which is what we call the state space equations. And when the switch is off, I have a different set of equations. Now these equations will keep on changing because we don't know at what you know, in a circuit, maybe the load change can happen, or the inductor, the states of the system itself is going to get solved. So to answer your question, the relation is within one time step, within that time frame, it has to calculate those matrices, state space matrices, and give out the output.
Okay, thank you, sir. So next question is there: how to deal real-time simulation of reconfiguration of a distribution system in the presence of nonlinear loads?
Uh, okay, so reconfiguration of real time. So can you repeat the question?
How to how to do real-time simulation of reconfiguration of a distribution system in the presence of nonlinear loads?
Uh, I mean, honestly, this looks to me like a research problem. I do not immediately know the answer for it, but I have one question though. So, if you have a non-linear load, the way to address that is you don't reconfigure your network because you have a non-linear load. You probably might be talking about power quality or harmonic filtering, such kind of application. So now it is the answer to this question. I would say simply like how you are going to you know simulate any other circuit. So real-time simulation has got nothing to do with what is the kind of intelligence that you are going to deploy. Real-time simulation, that's why the name of the simulation is also, it's an enabler. Basically it helps you to, or helps the designer to robustly design, test and validate, but it is not going to help you in making a reconfiguration of something. Now if you take so to answer your question in the same way how you are going to do a probably a microgrid analysis where you have a grid connected to islanded mode and there is a breaker which opens, in the same way reconfiguration or any applications, it depends on what kind of intelligence and what kind of thing that you are going to build. Yes, what real-time simulation is going to help is it is going to make sure that the plant or the network which is under study, it is emulating as close as possible to the actual hardware on the outside. So yeah.
Okay, so last question, sir. Is Homer software is applicable for hybrid microgrid taking Indian scenario into consideration in both islanding and grid connected mode?
uh, I am not that I mean I'm not that confident about Homer software because I have used Homer many years back, but more from a energy optimization and cost optimizations that level. But sorry, the question is more on hybrid.
The hybrid microgrid.
For a hybrid microgrid.
Mic-
Sorry, I do not honestly. I'm it's been many years since I used Homer, so I don't know what is its functionality right now. So I cannot comment on that. So
Okay, thank you, sir. So this is the end of the question and answer. Now I am handing over the session to Rajesh Patnaik, sir, to give the vote of thanks.
sure.
Dr. Stravada, sir.
Yes, sir.
Thank you very much, sir. Actually, you have enlightened most of the participants and also us, sir, regarding what is OpenRT, what is power system, and how we can do a real-time simulation for the power system. You have not only given the overview of a real-time simulation, but also explained so many examples. With the help of examples, you have explained so many case studies, and I think most of the participants would have been enlightened with an information with real time. What is the real time and what is the essence of real time simulation? And in this pandemic time, I thank you very much, sir, for accepting our invitation and giving us a chance to hear and listen from you. It's our honor, sir, and we are very much thankful to you, sir.
Yeah, thank you very much, sir, and thank you for organizing and calling me. Uh, and so, if you have any questions, as I was saying earlier, so please feel free to email me. And maybe I would have gone fast, as I was mentioning earlier. This in itself is a very big topic. Each one is a big topic by itself. But as a concluding statement, I just wanted to say it's real-time simulation is an enabler. It helps you to make robust designs. So with that, thank you very much, sir. I will sign off.
Thank you very
Thank
much,
you.
sir.
Thank you very much,
Thanks.
Raman.
Thank
Thank
you.
you.
Thank you, sir. Thanks a
Bye.
lot.
Thank you.
Bye. Good morning. Bye.
Also to the participants, thank you very much for your patience and listening the session. Now the feedback and quiz link will be activated, and strictly it is 4:15 now, so a half an hour time is given. So 4:45 we are going to log the quiz. So all of you are requested to please attend and submit the quiz before 4:45.
Patnaik, can we extend
This
till
ends the
5
second
o'clock?
day.
We will
Excuse me,
give
sir.
it till 5 o'clock. Let's give them 15 more.
Okay, sir, no problem. Okay, so the quiz will be locked at 5 p.m. So all of you are requested to please submit the quiz before 5 p.m. and all of you please enter the last digits of your reference number in the space provided. And that's it. It is the end of the second day. Hope again we'll join tomorrow at 1:45 p.m. Till then, stay safe, stay at home. Thank you very much. We're signing out.
Already 100 participants have given their feedbacks. They have participated. They have completed their feedback and quizzes. So that's good. Okay. Okay. See you participants tomorrow at the same time. We will try to start the session at 1:45, but try to be at 1:45. But we will start our session at 2 o'clock like today. Thank you. Thank you very much. Thank you all.
Thank
Bye.
you
Thank you.
also.
Thank you.